Welcome! In this session, we'll be tackling an exciting coding problem. Problem number 1590, make sum divisible by p. We'll break down the problem, explore various approaches, and work through a solution step by step. Let's dive in. The problem asks us to work with an integer array nums and an integer p. Our goal is to remove exactly one non-empty subarray from nums, such that the sum of the remaining elements in the array becomes divisible by p. If this is not possible, we should return -1. A subarray here is defined as a contiguous sequence of elements within the array, and it's important to note that we cannot remove the entire array. For the input, we are given an array nums with a length between 1 and 100,000, and each element as well as p can be as large as 1 billion. The output is an integer representing the minimum length of the subarray that needs to be removed to achieve the condition. If no such subarray exists, the output should be -1. Let's start by looking at some examples to better understand how this works. In the first example, nums is 3, 1, 4, 2, and p is 6. The sum of the array is 3 plus 1 plus 4 plus 2, which equals 10. When we divide 10 by 6, the remainder is 4. To remove this remainder, we need to find and remove a subarray whose sum is equal to 4. Here, the subarray, 4, meets this condition, and its length is 1. Therefore, the answer is 1. In the second example, nums is 6, 3, 5, 2, and p is 9. The sum of the array is 6 plus 3 plus 5 plus 2, which equals 16. Dividing 16 by 9 leaves a remainder of 7. To address this, we need to remove a subarray whose sum equals 7. The subarray, 5, 2, satisfies this requirement, and its length is 2. Thus, the answer for this case is 2. In the third example, nums is 1, 2, 3, and p is 3. The sum of the array is 1 plus 2 plus 3, which equals 6. When 6 is divided by 3, the remainder is 0. Since the sum is already divisible by 3, there is no need to remove any subarray. As a result, the answer is 0. In the fourth example, nums is 1, 2, 3, and p is 7. Here, the sum of the array is again 6, and dividing 6 by 7 leaves a remainder of 6. However, there is no subarray in nums whose sum equals 6. This means it is impossible to make the sum divisible by 7, so the answer is -1. These examples highlight the variety of scenarios we need to handle, where the remainder determines whether a subarray removal is feasible and, if so, the length of the shortest subarray. The constraints for this problem are significant. The length of nums can go up to 10^5, and both the elements of the array and the value of p can be as large as 10^9. This means we need an efficient solution to handle large inputs. A key insight for solving the problem is that the core challenge lies in finding the shortest subarray whose sum is equal to the remainder of total_sum %p. This insight helps us focus on the specific subarray that can remove the remainder, rather than examining all possible subarrays, which would be computationally expensive. By identifying this remainder and targeting subarrays that match it, we can significantly optimize our approach. To tackle this efficiently, we can use a combination of prefix sums and a hash map. The prefix sum allows us to calculate the cumulative sums of the array, while the hash map stores the remainders of these prefix sums modulo p. Using this structure, we can quickly find subarrays that meet the condition of having a sum equal to the remainder. If no such subarray is found after processing the entire array, we return -1. This combination of prefix sums and hash map ensures that our solution is both efficient and scalable for the given constraints. To tackle this problem, we first consider a brute force approach. The intuition here is straightforward: calculate the total sum of the array, then iterate through all possible subarrays, removing each one, and checking if the sum of the remaining elements is divisible by p. While this method is simple to conceptualize, it involves calculating the sum for every subarray, subtracting it from the total, and verifying divisibility, which leads to a time complexity of O(n cubed). This is because iterating over all subarrays takes O(n squared), and calculating their sums adds another O(n). The space complexity, however, is O(1), since no additional structures are used. Despite its simplicity, this approach is computationally expensive and impractical for large inputs, making it unsuitable for this problem. Now, a more efficient solution involves leveraging prefix sums and modulo arithmetic. By examining the properties of modulo operations, we reduce the problem to finding a subarray such that removing it leaves the remaining sum divisible by p. Specifically, if the total sum of the array is total, the condition simplifies to finding a subarray where subarray underscore sum %p equals total %p. This reduction forms the foundation for the optimized approach we'll discuss next. To efficiently find the required subarray, we use the prefix sum technique combined with a hash map. As we iterate through the array, we calculate the prefix sum modulo p at each index. The key observation is that if we encounter a situation where the difference between the current prefix sum and the remainder equals a multiple of p, then the subarray between the earlier occurrence and the current index satisfies the condition. Specifically, for a prefix sum value at index I, if prefix underscore sum I remainder %p was seen at an earlier index j, the subarray nums j plus 1 has the desired sum. To implement this, we compute the remainder of the total sum modulo p. We then use a hash map to store the last seen index of each prefix sum modulo p. As we iterate, we calculate the running prefix sum modulo p and check if the condition is satisfied. If it is, we calculate the subarray length and update our result if it's smaller than the current minimum. The algorithm continues until we've processed the entire array, at which point we return the smallest subarray length if found, or -1 otherwise. The time complexity here is O(n), since we traverse the array once while performing constant time operations with the hash map. The space complexity is O(n), due to the hash map storage. The chosen strategy for this problem is the optimized approach using prefix sums and modulo arithmetic. This method is not only more efficient than brute force but also scales well for large inputs. The key insight lies in reducing the problem to finding a subarray that satisfies a specific modulo condition, which can then be solved in linear time using hash maps. When comparing the two approaches, the brute force method is conceptually simple but computationally infeasible for larger datasets due to its cubic time complexity. In contrast, the optimized approach leverages mathematical properties to achieve a balance between clarity and performance, making it significantly faster and more practical. By adopting this strategy, we ensure that the solution is both efficient and capable of handling the constraints posed by the problem. In this problem, we are trying to find the smallest subarray that can be removed such that the sum of the remaining elements in the array is divisible by a given integer, p. If there is no such subarray, the algorithm needs to return -1. To begin addressing this, we first calculate the total sum of the array. This sum, referred to as total underscore sum, is the sum of all the elements in the array, and it serves as the starting point for our checks. Once we have the total sum, the next step is to determine if the array as a whole is already divisible by p. This is done by checking if total underscore sum %p equals 0. If it does, then the entire array satisfies the condition, and we don't need to remove any elements. In this case, the smallest subarray to remove has a length of 0, and the answer would simply be 0. However, if the total sum is not divisible, we need to explore further to identify the subarray that could make the remaining elements divisible by p. To find such a subarray, we need to iterate over all possible subarrays of the given array. This can be achieved by using two nested loops. The outer loop, represented by I, marks the starting index of the subarray, while the inner loop, represented by j, marks the ending index. For each of these subarrays, we calculate the sum of the subarray, which we call subarray underscore sum. Then, we determine the remaining sum by subtracting subarray underscore sum from total underscore sum, giving us remaining underscore sum. The next step is to check if this remaining underscore sum is divisible by p. If it is, we calculate the length of the current subarray as j I plus 1. Among all the subarrays that satisfy this condition, we keep track of the minimum length. At the end of this process, if no subarray meets the condition, we return -1 to indicate that it's not possible to make the sum divisible by p. Otherwise, we return the minimum length of the subarrays that meet the condition. While the brute force approach guarantees correctness by examining all possible subarrays, it is computationally expensive and inefficient for large arrays because of its nested loop structure. Specifically, the time complexity of this approach is O(n)^, where n is the length of the array. This high complexity arises because calculating the sum of a subarray in the inner loop takes n time, and iterating over all possible subarrays involves n squared iterations. Combining these factors results in n squared asterisk n, which is n cubed. To address this inefficiency, we can leverage a few key optimizations. First, by pre-computing prefix sums, we can reduce the time needed to calculate a subarray sum from n to 1, as the prefix sums allow us to retrieve subarray sums instantly. Additionally, we can use a hash map to optimize the algorithm further by avoiding the need to explicitly check all subarrays. These improvements significantly reduce the computational overhead, making the algorithm more suitable for larger input arrays. Finally, we need to consider edge cases to ensure the algorithm handles all scenarios correctly. If the array is empty, there are no elements to sum, so the algorithm should return -1. Another important edge case is when p equals 1. Since any integer is divisible by 1, the answer in this case is always 0, as no subarray needs to be removed. If all elements in the array are 0, the answer depends on the value of p. If p is not 0, then the total sum of the array is already divisible by p, and the answer is 0. In terms of complexity analysis, the brute force approach remains n cubed in time due to the nested loops and subarray sum calculation, while the space complexity is 1, as it only uses a few variables to store intermediate results. These observations highlight the importance of pursuing more efficient algorithms for larger inputs, as the brute force approach becomes impractical in such cases. Here, we start by defining the min-subarray function inside our solution class. The function takes two inputs, nums, which is the array of integers, and p, the divisor. First, we calculate the total sum of the array and find the remainder when this sum is divided by p. If the remainder is 0, it means the entire array is already divisible by p, so there's no need to remove any subarray, and we return 0. Next, we initialize variables to help us with our computation. Prefix _sum will keep track of the running sum of the array, min_length is set to the length of the array as a starting point for our minimum subarray length, and prefix _map is a dictionary that maps prefix sums modulo p to their respective indices. This will help us efficiently track and check for subarrays that can make the total sum divisible by p. Now, we iterate over the array using a for loop. For each number, we update the prefix _sum and calculate its modulo p value, which gives us the current mod value. Next, we compute the target _mod, which represents the modulo value we need to find in order to adjust the total sum to be divisible by p. If this target _mod exists in our prefix _map, it means we can potentially remove a subarray to achieve divisibility, so we update min_length with the smaller of its current value and the distance between the current index and the index stored in the map. Finally, we update the prefix _map with the current mod value and its index. After completing the loop, we check if a valid subarray was found. If min_length is still equal to the length of the array, it means no such subarray exists, so we return -1. Otherwise, we return the min_length, which represents the smallest subarray that can be removed to make the total sum divisible by p. This approach ensures that we efficiently find the solution by leveraging the prefix sum technique and a hash map to achieve an optimal time complexity. By focusing on modular arithmetic, we avoid having to check all subarrays explicitly, making the algorithm scalable for larger inputs. Here, we begin by importing the necessary utilities and defining our solution class. Within the class, the method min_subarray is defined to solve the problem. The first step is to calculate the total sum of the array. This sum is then used to determine the remainder when divided by p. If the remainder is 0, it means the total sum is already divisible by p, so we can return 0 immediately, as no subarray needs to be removed. Next, we initialize a hash map called prefix map to store prefix sums modulo p and their corresponding indices. The map starts with an entry for mod value 0 at index -1 to handle cases where the subarray starts from the beginning of the array. We also initialize min length to the full length of the array, as we aim to minimize this value. Then, we define a prefix sum variable which will keep track of the cumulative sum as we iterate through the array. In the loop, we add the current element to prefix sum and compute the modulo of this sum with p. To find the desired subarray, we calculate the target modulo that would balance out the remainder and ensure it's positive using modular arithmetic. Next, we check if the calculated target modulo exists in our prefix map. If it does, it means there is a prefix subarray that, when removed, would make the remaining sum divisible by p. In this case, we update min-length by comparing its current value with the difference between the current index and the index stored in the map for the target modulo. This gives the length of the candidate subarray. After processing the current element, we update the prefix map by storing the current modulo and its index, ensuring we keep track of all potential prefix sums for subsequent iterations. Finally, after the loop completes, we return min-length if it was updated to a value less than the array length. Otherwise, if no valid subarray was found, we return -1 to indicate it's not possible to make the sum divisible by p. This implementation efficiently handles the problem using modular arithmetic and a hash map for constant time lookups, ensuring an optimal solution. Let's start with the example where nums equals 3, 1, 4, 2, and p equals 6. First, we calculate the total sum of nums, which is 10. Next, we find the remainder of dividing this total sum by p. Since 10 modulo 6 equals 4, the remainder is not 0, meaning we need to proceed with our logic to find a subarray whose removal makes the sum divisible by 6. We initialize the prefix sum to 0, set the minimum length to the size of the array, which is 4, and begin with a prefix map containing just the entry 0, -1. This map helps us efficiently track indices of prefix sums modulo p. Now, in the first iteration with I equal to 0 and number equal to 3, we update the prefix sum, which becomes 3. The current modulo of this prefix sum is 3. To find the target modulo, we subtract the remainder, 4, from the current modulo, and then take the result modulo p. This gives us a target modulo of 5. Since this target modulo is not yet in the prefix map, we simply add the current modulo, 3, with its index, 0, to the map. In the second iteration, where I equals 1 and number equals 1, we update the prefix sum to 4. The current modulo of this prefix sum is also 4. Calculating the target modulo as the difference between the current modulo and the remainder, we get 0. This target modulo is already in the prefix map at index -1. Using this, we calculate the subarray length as the difference between the current index and the stored index, which gives us a length of 2. Since this is smaller than the minimum length of 4, we update the minimum length to 2. Then, we add the current modulo, 4, with its index, 1, to the prefix map. Moving to the third iteration, when I equals 2 and number equals 4, we update the prefix sum to 8. The current modulo of this prefix sum is now 2. The target modulo is computed as 4, which is already in the prefix map at index 1. Using this, we calculate the subarray length as 1, which is smaller than the current minimum length of 2, so we update the minimum length to 1. Finally, we add the current modulo, 2, with its index, 2, to the prefix map. In the fourth and final iteration, where I equals 3 and number equals 2, we update the prefix sum to 10. The current modulo of this prefix sum is 4. The target modulo, calculated as 0, is found in the prefix map at index -1. Using this, we calculate the subarray length as 4. However, the minimum length remains 1, as it's already smaller than this new subarray length. We then update the prefix map to include the current modulo, 4, with its index, 3. With all iterations complete, the smallest subarray length that can be removed to make the sum divisible by 6 is 1. Thus, we return the final result of 1. Now, let's consider the second example where nums equals 6, 3, 5, 2, and p equals 9. The total sum of nums is 16, and the remainder when dividing this sum by p is 7. With the remainder not equal to 0, we initialize the prefix sum to 0, set the minimum length to 4, and begin with a prefix map containing 0, -1. In the first iteration, where I equals 0 and number equals 6, the prefix sum becomes 6, and the current modulo is also 6. The target modulo, calculated as 8, is not in the prefix map, so we add 6 with its index, 0, to the map. In the second iteration, where I equals 1 and number equals 3, the prefix sum updates to 9, with a current modulo of 0. The target modulo is calculated as 2, which is not in the map, so we add 0 with its index, 1, to the map. In the third iteration, where I equals 2 and number equals 5, the prefix sum becomes 14, and the current modulo is 5. The target modulo is calculated as 7, which is not yet in the map, so we add 5 with its index, 2, to the map. Finally, in the fourth iteration, where I equals 3 and number equals 2, the prefix sum becomes 16, and the current modulo is 7. The target modulo, calculated as 0, is found in the prefix map at index 1. This gives us a subarray length of 2, which updates the minimum length to 2. The smallest subarray length to remove is therefore 2. In the final example, nums equals 1, 2, 3, and p equals 3. The total sum of nums is 6, and the remainder when dividing this sum by p is 0. Since the remainder is 0, the entire array is already divisible by 3, so there's no need to remove any subarray. In this case, we simply return 0 as the result. The time complexity of our solution is O, n, where n represents the length of the input array nums. This complexity arises from two main components. First, calculating the total sum of the array using sum, nums, requires O, n, time since it iterates through all elements of the array once. Second, the main loop also iterates through the array once, performing constant time operations for each element. These operations include updating prefix underscore sum, computing the current underscore mod and target underscore mod, and accessing or updating the dictionary prefix underscore map. Accessing and updating the dictionary takes average case O1 time due to efficient hashing. Combining these steps, the total time complexity becomes O n from the sum calculation and O n from the loop, resulting in an overall time complexity of O n. The space complexity of the solution is O n, which stems from the use of a dictionary called prefix underscore map. This dictionary stores mappings of prefix sums modulo p to their respective indices. In the worst-case scenario, the dictionary could hold up to n entries, one for each element in the array. Aside from this, the algorithm uses a small number of scalar variables such as total underscore sum, remainder, prefix underscore sum, current underscore mod, target underscore mod, and min underscore length. These variables require constant space, or O1. Therefore, the overall space complexity is dominated by the dictionary, resulting in O n. When comparing the optimized solution to a brute force approach, the difference in efficiency becomes clear. A naive solution would involve iterating through all possible subarrays of nums to check if removing each subarray results in a sum divisible by p. Generating all subarrays through two nested loops would take O n squared time, and computing the sum of each subarray would add another O n, leading to a total time complexity of O n cubed. In contrast, the optimized solution leverages prefix sums and a hash map to avoid unnecessary computations. By efficiently identifying the smallest subarray that meets the condition, the optimized solution achieves a significant improvement, reducing both the time complexity to O n and the space complexity to O n. The algorithm's efficiency can be analyzed across different scenarios. In the best case, if the total sum of nums is already divisible by p, the algorithm can terminate early after computing the sum, resulting in a time complexity of O n. In the average case, for a randomly distributed input, the algorithm processes the entire array and performs constant time operations for each element, maintaining a time complexity of O n. Finally, in the worst case, the algorithm still processes the entire array and may populate the dictionary with up to n entries. Despite this, the time and space complexities remain O n. Mathematically, the key operations involve updating prefix sums and accessing the hash map. Each of these is performed in O1 time per element, leading to a total time complexity of O n asterisk O1 equals O n. When tackling this problem, there are several common mistakes that can trip you up if you're not careful. First, forgetting to handle edge cases is a frequent issue. For example, you need to account for scenarios like empty arrays, arrays with only one element, or cases where the value of p is larger than the total sum of the array. Neglecting these can lead to incorrect results or even runtime errors. Another common pitfall is ignoring the properties of modulo arithmetic. Remember, modulo operations follow specific rules, such as a plus b, %p equals, %p, plus, b %p. If you don't take advantage of these properties, you might end up performing unnecessary computations, making your solution inefficient. Speaking of inefficiency, relying on brute force approaches is another mistake. Iterating over all possible subarrays results in time complexities like O, n cubed, or O, n squared, which are impractical for larger inputs, such as when n is 100,000. Finally, implementation errors can occur when using advanced techniques like sliding windows or prefix sums. Failing to update the window correctly or missing edge cases, like when the subarray wraps around, can lead to incorrect answers. Overcomplicating your solution is another risk. While advanced data structures like segment trees or Fenwick trees might seem appealing, they're often unnecessary here, as simpler methods like hashing or prefix sums are sufficient. Now, in the context of interviews, it's important to understand what interviewers are looking for when solving this problem. They typically expect you to go beyond brute force approaches. For example, using hashing to store prefix sums and achieve O, n, or O, n log n, time complexity demonstrates a strong grasp of the problem. Mastery of modulo arithmetic is also crucial, as many problems rely on these properties. You should be able to explain how they work and why they're useful in your solution. Additionally, be prepared to discuss trade-offs between space and time. Using a hash map, for instance, can improve runtime but increases space usage. It's essential to show that you understand these trade-offs. Finally, clear communication is key. As you optimize your solution, articulate your thought process step by step. This makes it easier for interviewers to follow your reasoning and assess your problem-solving skills. To broaden your understanding, it helps to look at related problems. For example, LeetCode 525, contiguous array, uses prefix sums with hash maps. Similarly, LeetCode 560, subarray sum equals k, applies the same strategy. LeetCode 974, subarray sums divisible by k, focuses on modulo arithmetic combined with hashing, making it particularly relevant. Another example is LeetCode 1248, count number of nice subarrays, which takes a variation of the prefix sum approach. Exploring these problems can help solidify your grasp of the techniques involved. As for alternative approaches, the prefix sum with hashing method is a popular choice because it achieves O, n, time complexity, though it requires additional space. Sliding window techniques can sometimes work, especially for simpler variations, but they might struggle with modular constraints, limiting their applicability. Lastly, there's the option to optimize brute force by pre-computing prefix sums. This reduces the time complexity to O, n squared, but it's still too slow for large inputs, so it's generally not the best choice for this problem. Finally, it's important to weigh the trade-offs when deciding on an approach. Using hash maps can significantly reduce the time complexity of your solution, but it comes at the cost of increased space usage. On the other hand, a sliding window approach might use less space but could fail to handle certain variations of the problem, such as those involving modular constraints. Another trade-off to consider is readability versus optimization. In some interview scenarios, a simpler O, n squared, solution might be acceptable if the input size is small, as it's easier to explain and implement. However, for larger inputs, always aim for an O, n solution to ensure scalability. Being mindful of these trade-offs and discussing them clearly during an interview demonstrates a mature understanding of problem-solving and algorithm design. Great job! We've successfully solved problem number 1590, make sum divisible by p, by using modular arithmetic and hash maps. Remember the key insights about modular arithmetic and hash map efficiency. Keep practicing, and I'll see you in the next session. Don't forget to like and subscribe for more content. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!